This is Cindy Fuhrer, and today we're going to talk about how to calculate empirical and molecular formulas. We're going to do 3 different types of problems, and to do all 3 different types, you're going to need a calculator and a periodic table. Our first problem is how to find the empirical formula if the sample of a compound contains 13.5 grams of calcium, 10.8 grams of oxygen, and 0.65 grams of hydrogen. Okay, the first thing we're going to want to do is to find the moles of each of these grams, because formulas have ratios of whole numbers in moles. So we're going to start off with the 13.5 grams of calcium. Look on the periodic table and find the molar mass of calcium, which is approximately 40.08 grams in 1 mole. It may vary a little bit depending on what periodic table you have. Use our calculator and take 13.5 and divide it by the 40, and we get 0.337 moles of calcium. Now we're going to continue and do this with each one of the elements until you've done it with all the elements. So now we're going to take 10.8 grams of oxygen, divide it by the molar mass of oxygen out the periodic table, and we find out that there's 0.675 moles of oxygen. Now we've got to continue and do this also. So we have 0.675 grams of hydrogen, and off the periodic table is approximately 1.008 grams of hydrogen in 1 mole of hydrogen. Dividing this out, we get 0.668 moles of hydrogen. Now we want to do ratios. To do the ratios, you're always going to pick the smallest moles. And the smallest moles will be in the denominator of each of the ratios. So we'll always have one ratio less than the number of elements that we have. So we're going to take our smallest moles, which is our 0.337 moles of calcium, and we're going to put it in the denominator. So 0.337 moles of calcium. And on top, we're going to put one of the other two. So we're going to put the 0.675 moles of oxygen. And we're just going to divide those two numbers. And when we divide those two numbers, we get 2 approximately. So it is basically means that there are 2 oxygens for every 1 calcium in our formula. Our second ratio, we're going to keep 0.337 on the bottom. You always keep the smallest one still on the bottom. It should be the same for every ratio. And we're going to use our other moles of hydrogen up here, so 0.668 moles of hydrogen. And when we divide those numbers, we get 1.98. Okay, so we're going to round to our nearest whole number, and that will give us 2. What that's saying is for every 2 hydrogens, we get 1 calcium. So now what we're going to do, we're going to put that all together. We're going to write a formula with our ratio said that there was only 1 calcium, there was 2 oxygens, and there was 2 hydrogens. When you first begin this, a lot of people have trouble with what order do I put all the elements in. And you want to start with the metal in the first one, and then your nonmetals. It may be that you will recognize a polyatomic ion. For example, if we take out the 2's here and put them behind it, we'll recognize that OH is a polyatomic ion hydroxide. Otherwise, most of the time it'll work just to go from left to right across the periodic table and put them in order with that, with hydrogen in this time being a little bit of an exception. Okay, our second problem, we're going to find the empirical formula of a compound containing 40.6% carbon, 5.1% hydrogen, and 54.2% oxygen. Okay, now this one's obviously different because it contains percents, and we always need to start with grams and convert it to moles and then do the mole-mole ratio. So what we're going to do is we're going to assume 100 grams, and by assuming 100 grams and working with percents, we know that 40.6% of carbon becomes 40.6 grams of carbon. 5.1% of hydrogen becomes 5.1 grams of hydrogen. And 54.2% of oxygen will become 54.2 grams of oxygen. Now what we want to do, these grams, and convert them to moles. So we're going to take the 40.6 grams of carbon, divide it by the molar mass of carbon, and we get 3.38 moles of carbon. Then we want to take the 5.1 grams of hydrogen, divide it by the molar mass of hydrogen, and we get 5.1 moles of hydrogen. Finally, we take 54.2 grams of oxygen, and you do this to use however many elements you have. You got to find the moles of all of them. And this is 3.39 moles of oxygen. Okay, so now what we found was 3.38 moles of carbon, 5.1 moles of hydrogen, and 3.39 moles of oxygen. So now we're going to set up our ratios again using the smallest one on the bottom all the time. So we're going to use the 3.38 moles of carbon on the bottom. So I'm going to take 5.1 moles of hydrogen and put it on top over 3.38 moles of carbon. And I divide that out and I get 1.5, which turning it into a fraction is 3/2. Then I'm going to take 3.39 moles of oxygen and put it over 3.38 moles of carbon. And that's basically a 1-to-1 ratio. So for every 1 mole of oxygen, we have 1 mole of carbon. Okay, now we cannot have in one two of carbon and another one have 1 of carbon. So we have to get a common denominator. So we're going to have to multiply this one here by 2 on the top and bottom. So we get a common denominator of 2 for both. So here we have 2 moles of oxygen for every 2 moles of carbon. Up here we have 3 hydrogens for every 2 carbon. These really wouldn't be moles. They were really just a ratio of 3 hydrogens for 2 carbons, 2 oxygens for 2 carbons. So we can leave those moles out. Okay, the last thing we need to do to solve the problem is to write the formula. When it's an organic compound, or in other words, it contains carbon, you're always going to want to write carbon first. In the carbon, there was 2 there, so we put C2. Then it's common to put hydrogen second. Hydrogen is a 3, and then the oxygen would go last, so O2. So our formula is C2H3O2, and we're done solving the problem. Okay, now we're going to do the longest problem because these problems involve finding both the empirical and molecular formula. First, we have a problem up here. Caffeine has the composition of 49.48% carbon, 5.19% hydrogen, 16.48% oxygen, and 28.85% nitrogen. And it says to find the empirical and molecular formula. Now, one additional thing they need to give us is we need to know the formula mass or the molar mass. So the molar mass of caffeine in this problem is 194.9 grams per mole. We will need that at the very end. Okay, so the very first thing we're going to do is exactly what we did in the last problem. We're going to take each percent, make it into grams, and then convert each grams to moles. So we'll start with carbon. The 49.48% becomes grams, and then we divide it by its molar mass, and we find how many moles of carbon we have. And if you divide that out, you get 4.120 moles of carbon. We take the percent of hydrogen. The percent of hydrogen becomes grams of hydrogen. We divide it by the molar mass of hydrogen, and we find the moles of hydrogen, which is 5.15 moles of hydrogen. Okay, now continuing on, we're going to find the 16.48% of oxygen. We're going to make that into grams, and we're going to divide that by the molar mass of oxygen. And that gives us 1.030 moles of oxygen. And finally, the 28.85% nitrogen becomes 28.85 grams of nitrogen. And we're going to divide that by the molar mass of nitrogen. And then we will know the moles of nitrogen, which is 2.060 moles of nitrogen. Now, it's really important that you keep your significant figures through all this. Okay, then we look to see which one has the lowest amount, so we can make our ratios. The lowest amount is with the oxygen. So we're going to have oxygen always on the bottom. Okay, so I'm going to start with the very first one, carbon. We had 4.120 moles of carbon, and I'm going to divide it by that 1.030 moles of oxygen. And that gives us a ratio of 4. You divide that, it's 4, so that's the same thing as 4 to 1. So there's 4 carbons for every 1 oxygen. Now we're going to continue on and do the next ratio. We're going to take the second moles we found, which was the moles of hydrogen, divide it by the smallest one, which is the moles of oxygen, and we get 5. So it's 5 to 1. 5 hydrogens for every 1 oxygen molecule. And finally, we'll do the nitrogen, which was 2.060 moles of nitrogen divided by 1.030 moles of hydrogen. And you get 2, which is same as 2 to 1 ratio. So 2 nitrogens for every 1 hydrogen. Now we're ready to write the formula. Remember we said if you have carbon, we're always going to put carbon first because it's an organic structure. So the very first thing that we're going to put is C, and there was a 4 of them because it said C4 for every 1 oxygen. Then we're going to put the hydrogen here. So hydrogen 5 because of the 5 right there. And then nitrogen 2, so N2. And finally, we're going to put the oxygen, which should be just 1, because all the denominators had 1. Now this is the empirical formula. Now what we need to find is the molecular formula. For the molecular formula, we need to know what the molar mass is. The molar mass, or the formula mass. So it was told that there was 194.9 grams per 1 mole. We know their empirical formula is C4H5N2O. So what we want to know is, does this empirical formula, what does it weigh? So we want to find the mass of this formula. So off the periodic table, we're going to take carbon's mass times 4, plus hydrogen's mass times 5, plus nitrogen's mass times 2, plus 1 oxygen's mass. And we find out its mass is 97.1 grams per mole. Now, if we do a ratio of the molar mass to the empirical formula mass, we'll find out how much larger the molecular formula is. So you take 194.9 and you divide it by the mass of the empirical formula. And you divide that out, it comes basically out to be 2. That's telling us that our empirical formula is twice, the molecular formula is twice as big as empirical formula. So now we need to rewrite. We're going to take each one of these subscripts that are in the empirical formula, remember this is the empirical formula, and we're going to multiply it by 2. So we get C8, H10, and 4O2. And this is our molecular formula.